This lecture is one of the deceptively simple ones. Students look at impulse, step, and ramp and think, I already know these shapes, and then they memorize a few responses. But if you do only that, you miss the real structure. The S domain gives us a different way to think. An input is not primarily a drawing in time. An input is an algebraic object, x. The system is h of s. The output is y of s. And for linear time invariant systems, under the transfer function viewpoint, the relationship is brutally simple. Y of s is equal to h of s times x of s. So here's the thesis. Impulse, step, and ramp do not change your system's modes. They do not change your poles. They only weight those modes differently, mostly by adding poles at the origin. And the origin in the S-plane corresponds to a slow, steady behavior. So these three inputs are really three different questions we ask the same system. Impulse, show me your modes correctly. Step, where do you settle? Ramp, can you track a command that keeps growing? That's the lens for the entire lecture. So let's build a mental workflow. When you see y of s equal to h of x into x of s, do not rush to invert. That's the student reflex. I need y of t, so let me do the partial fractions immediately. But that often turns the whole subject into template memorization. Instead, an engineer asks, what poles come from the system? And what poles come from the input representation? Because the input can add poles at the origin, and those origin poles strongly bias the outcome towards low frequency, long term behavior. So, this multiplication is not algebra for its own sake, it is prediction. Even before inversion, you can say, will the response be bounded? Will it settle to a constant? Will it grow linearly? Will it blow up like t squared? Those are structural questions, and the S domain answers them quickly. Now, impulse is the cleanest input in the S domain because S of x of s is 1. That means it adds no poles anywhere, especially not at the origin. So it does not bias the system towards slow or fast behavior. It's just let the system speak. You may have heard that impulse excites all frequencies equally. The safer structural interpretation is impulse does not add any extra weighting like 1 by s or 1 by s squared. Therefore, the output becomes h of s directly. In other words, impulse reveals the system's structure cleanly. In real life, we cannot create an ideal impulse, but we can approximate it with a very short pulse whose area is fixed. That is what engineers do in a system. They apply a sharp excitation and watch how the system rings down. Now, because impulse makes y of s equal to h of s, the impulse response h of t is simply the inverse Laplace of h of s. That is why impulse response is called the system's fingerprint. Now, every pole of h of s corresponds to mode in time. A real pole gives a decaying exponential. A complex pair gives a decaying sinusoid. So when someone shows you an impulse response, you should immediately think that waveform is a visible mixture of all system modes. One misconception I want to kill here. Impulse response is not the same thing as response due to initial energy. Those are different ideas. We are keeping to the transfer function viewpoint. The impulse response is the output when the input is an impulse and the initial conditions are 0. So let's do the simplest first order case. H of s equal to 1 by s plus a. With impulse input, y of s is equal to h of s is equal to 1 by s plus a, and therefore the inverse Laplace of that is e power minus at u of t. What is the interpretation? There is one pole, so there is one mode. The system cannot do anything more complicated than a single exponential decay. There is no oscillation. There is no overshoot. There is only one time scale, the time constant 1 by a. Now here's a common student mistake, confusing a with tau. A is the rate, tau is the time. They are reciprocals. The moment you internalize this, first order systems become intuitive. Now the step input. The step in Laplace is x of s equal to 1 by s. Now this looks simple, but it is actually demanding because it introduces a pole at the origin. That origin pole means the input is heavily weighted down towards the lower frequency, which corresponds to steady behavior. Real life is full of steps: turning on a circuit, changing a reference voltage, suddenly applying a force, moving a command from one value to another. Step tests are used everywhere because they answer the question, does the system settle? And if it does, where does it settle? But here is the structural discipline. The step does not change the system. Poles. It adds a pole in the input representation. So the output expression changes because x of s changes, not because the system has changed. So for a step, y of s is equal to h of s by s. I want you to see the meaning of that division by s. It is literally saying your output now contains one extra pole at the origin because the input contains it. That is why the modes near s is equal to 0 dominate step behavior. The input is magnifying the near origin region. And what lives near s is equal to 0? DC and steady state behavior. Students often treat this as abstract, but the time domain intuition is simple. Step is asking for a final value. Final value is a DC concept. DC corresponds to S close to 0. So step forces you to care about the S close to 0 behavior. Now, for a stable second order system, there are two system poles in the left half. Those two modes define the transient behavior, whether it rings, overshoots, how quickly it settles, etc. Now, when we apply a step, we multiply it by 1 by s. That does not move the system poles, it just adds an original pole that emphasizes low frequency content and makes the long-term value more prominent in algebra. A key misconception is, if step adds a pole, does the system become third order? No, the system is still second order. The output expression has an extra pole because the input requires an integration like weighting. But the internal memory count of the system has not changed. This distinction is essential when you move later into control theory. Now ramp is the next step, x of s equal to 1 by s squared. That means a ramp adds a double pole at the origin, even stronger low frequency emphasis than the step. And ramp corresponds to real life engineering situations, constant velocity command, a reference that increases steadily, or even error accumulation. Ramp tests whether the system can track something that keeps moving. A very dangerous student misconception is ramp is just a slow step. It isn't. A slow step still asks for a constant final value. Ramp asks for an output that grows linearly with time. That's a different kind of demand and it stresses the low frequency structure far more. Now with ramp, y of s is equal to h of s by s squared. The S-domain interpretation is the origin region dominates even more strongly. If your system has insufficient low-frequency authority, the output will lag more and more behind the ramp. The key concept here is tracking error. For ramp tracking to be good, the output must eventually have the same slope as the input. Otherwise, the gap grows without bound. Even without doing full inversion, you can often predict whether the system can track ramps by looking for an integrator like behavior or low frequency gain. So, ramp is a stress test of the system's low frequency behavior and its ability to follow changing commands. And this is where the S domain becomes almost brutally predictive. If h of s already has a pole at the origin, meaning the system behaves like 1 by s at low frequency, and you multiply by 1 by s squared of the ramp function, you get y of s is equal to 1 by s cubed. Now the inverse Laplace of 1 by s cubed is t squared by 2. That's quadratic growth. It is unbounded and it accelerates upwards. So the conclusion is immediate. Ramp plus an integrator like system can lead to runaway polynomial growth in the output. This is a place where students get confused and say, but integrators are good for steady state error. Yes, they are for steps. Ramp is harder. This is why control engineers classify systems by type and analyze step versus ramp errors separately. Now let's summarize this philosophy. Impulse do not change the system structure. Sorry, inputs do not change the system structure. The system poles, its modes are properties of h of s. What inputs do is weight these modes and reveal robustness or weaknesses. Impulse is neutral and reveals the mode mixture. Step adds origin pole, pushing attention to steady state and DC gain. Ramp adds two origin poles, pushing attention to tracking and its low frequency behavior. If you keep this in your head, input is equal to weighting, you stop making the classic mistakes that haunt people for years. Now, this is a teaching statement about method. If you invert too early, you can get a correct time expression but learn nothing. You start memorizing partial fraction templates and you won't know what terms correspond to transient modes, what terms correspond to steady behavior, and what part comes from the input. Engineers do the opposite. They inspect structure, predict dominant behaviors, and then invert if needed. The S domain is a reasoning tool, not just a computational tool. Once you see that, you become much faster and much more accurate. Let's just hit the misconceptions head on. Impulse response is useless? No, it's the system's fingerprint. Step response defines the system? No, it's one experiment. Ramp is a source step? No, it stresses tracking of an unbounded command. Time response must be computed to understand behavior? No, the S domain lets you predict a lot without full inversion. And the big one, step and ramp change system order. No, they change y of s because x of s changes. The system remains the same. Now use this reflection as a self-test. The most important takeaway is origin pole counting. Impulse has 0 origin poles, reveals modes. Step has 1 origin pole, emphasizes s equal to 0, steady state. 2 origin poles for the ramp, stresses s equal to 0 and tracking of growing command. So if h of s has a pole at the origin and you apply a ramp, y of s has 3 origin poles and the time response grows like t squared by 2. That is a kind of statement you should be able to say without any anxiety because it's structural. Finally, why is early inversion dangerous? Because it replaces understanding with algebra. Predict first, compute second. Now we'll look at this very clearly by doing the math. Let's look at one system with three inputs. Let's start with h of s equal to 1 by s plus 2. So it has one pole at minus 2. It's stable with a time constant of 0.5 seconds. So if I apply an impulse input, that is with x of s equal to 1, then y of s becomes 1 by s plus 2. And therefore, you get y of t as e power minus 2t ut. That is, the output is a decaying exponential as expected of the first order. Now when I apply a step input of x of s as 1 by s, then I get y of s as 1 by s into s plus 2. Break down into partial fractions, give you 1 by s minus 1 by s plus 2. And so you get in time domain half of 1 minus e power minus 2t. Notice this is the same decaying exponential is present. So the same mode is present between the two. But now there is a constant final value because the input introduced at the origin pole. The difference in the two. Now when you're given a ramp input, 1 by s squared, ramp input, so y of s becomes 1 by s squared into s plus 2. You decompose it as a by s plus b by s squared by c by s plus 2, partial fractions. And you give a is equal to 1 by 4, half and 1 by 4. And so you get y of t as minus 1 by 4 plus half t plus 1/4 of e power minus 2t. So again, the same mode appears. The long-term demand is now linear growth. This is the cleanest demonstration that inputs weigh modes. They do not change them. So here you can look at the error rate of the ramp, and you see that as t tends to infinity, the error also grows unbounded. So a type 0 system cannot track a ramp with a bounded error. Right? As time grows, this exponential term dies in this expression, but the error grows without a bound. Now, this is a foundational concept for control and tracking. Without sufficient low frequency authority, ramps create ever-growing error. Now here's one rule you can keep forever: origin pole counting. Let n0 be the number of poles at s is equal to 0. Then n0 of y is nothing but the n0 of h plus the n0 of x. The impulse adds 1, 0, the step adds 1, and the ramp adds 2. And origin poles correspond to polynomial growth in time. One origin pole corresponds to constants, 2 corresponds to ramps, 3 corresponds to t squared growth. So when you see h of s as 1 by s and ramp x of s as 1 by s squared, you instantly know y of s as 1 by s cubed, and the time domain term is t squared by 2. This is not memorization, it's structure.